Hey everyone. So this is going to be the very first video in the Chapter 7 series where we're going to be looking at reactions that form alkenes. Okay, so these are reactions that start with either an alkyl halide or an alcohol, and they form an alkene, a double bond. All right, that's what we're concerned about in Chapter 7. So there's three reactions. There's E2, E1, and dehydration. This very first video that we're going to be doing here is going to be over E2. All right. So just like with the SN reactions, SN1 and SN2, with these E2 and E1 videos, the very first thing that I want to do with these videos is look at the specifics of the reaction. So we kind of have like a nice bullet point list of exactly what we're worried about whenever it comes to those reactions. Okay. So there's a few things that I think are important whenever we look at E2. So I'm going to make a list of these, and then after that, we can kind of start getting going on the actual reaction. So the very first thing is that we prefer a 3-degree alkyl halide over 2-degree over 1-degree. Okay, so 3-degree alkyl halides for E2 are the best, and then 2 degrees next, and 1 degrees last. Right, so that's similar to that's similar to SN1. Right. The next thing is that this requires a strong base. All right. So similar to SN2, whenever we had a strong nucleophile, with E2, we have a strong base. All right. And notice that I said base and I didn't say nucleophile. Bases and nucleophiles are not always the same thing. There's some things that are nucleophiles that aren't good bases and vice versa. So just try and keep that in mind. The next thing is that the solvent is normally the conjugate acid of the base. I'll have to excuse my handwriting. So what does this mean? Again, we'll get into this in a second. I just want to get all this stuff written down just so that we kind of know exactly what's up. So now let's look at the rate equation. So the rate equation is just like the SN2 rate equation. So the rate equation has alkyl halide, so our rate constant, times concentration of the alkyl halide, times the concentration of the base. Okay, so we have alkyl halide and base, both in there, just like SN2. All right. Another thing that's similar to SN2 is that this is concerted. This is a concerted reaction, concerted mechanism. So that means it happens in one step. So this is concerted reaction. So that means it happens in one step. That also means that I can't have a carbocation, so there's no rearrangements. No rearrangements at all in this reaction. All right. And then these last two things we're going to talk about more a little bit later, but I'm just going to write them down now. So the halogen that's leaving and the hydrogen that's being taken must be anticoplanar. Which is also sometimes called anti-periplanar. So if you see anticoplanar or anti-periplanar, that's the same thing. What does that mean? Well, that just means that they are 180 degrees apart from each other. And we'll look at that a little bit more later. Then the very final thing is that E2 forms the Zaitsev product as the major product. Unless the base is bulky. All right, so we have a bulky base. We don't form the Zaitsev product. We form a different product. But If the base is not bulky, we just have a regular base, then we do form the ZZ product. All right. So again, we'll worry about what that means in just a second. So let's take a look at a couple examples here really quickly. So very first thing we'll look at is this alkyl halide here. It's alkyl bromide. And we're going to put it through with sodium methoxide and methanol as a solvent. So how do I know that this is E2? Well, there's a couple things. So like we said earlier, it prefers 3 degree over 2 degree over 1 degree. So this is a 2 degree alkyl halide. So it could go through E2. But looking at my base right here, NaOCH3, that's also a nucleophile, right? Methoxide is a perfectly fine nucleophile. So this could go through SN2. So how exactly do we know that this isn't SN2? Well, I know that because of the solvent. All right. So earlier I said that the solvent is the conjugate acid of whatever base we're using. So in this case, the base we're using is OCH3 minus, right, methoxide. So if I take that and I add a hydrogen to get the conjugate acid, then that's going to give me OCH or HOCH3, excuse me. So this is just methanol, right? So HOCH3 is methanol. So that's my solvent. So this is specifically what's telling me that this is an E2 reaction. So if my solvent is the conjugate acid, so I just added a hydrogen compared to the base, there's a very, very good chance that it is E2, as long as the base is strong and as long as the degree works out, right? As long as it's, 3 degree or 2 degree, all right? Then it's almost certainly E2, all right? So let's take a look at the mechanism, and then we'll worry about what exactly the product is, all right? So this is my mechanism for this reaction. So I have my bromine here with my lone pairs around it. And then my base, OCH3 minus, has 3 lone pairs around this oxygen. All right. So remember a base, in this case, we're talking about a Bronsted base. So a Bronsted base is anything that accepts a proton. So it's accepting a proton or a hydrogen, right? And so that's what's going to be happening in this reaction. So I'm going to be taking a hydrogen off of this molecule to form a double bond. So then the question is, where do I take the hydrogen from? Like there's a lot of hydrogens in this molecule right here, right? So where does that hydrogen come from? Well, that's really the crux of the question, right? So the only places that I can take a hydrogen from are from carbons adjacent to the carbon that's connected to the halogen. So this carbon right here that my cursor is over is connected to the halogen, right? So this carbon has the bromine on it. So that means that I can take a hydrogen from here because this has 3 hydrogens on it and it's adjacent. This is an adjacent carbon. But I can also take a hydrogen from here as well, right? This is also an adjacent carbon because it's right beside it, right? So I can take a hydrogen from here or here. These are the only places I can take a hydrogen from. So how do I know which one to take? Well, we'll get into that in a second, but I'm going to take the correct one. So the correct one here is this one, but I could take any of them, but this is the hydrogen that I should take. And we'll talk about why after we draw the mechanism. So I take this hydrogen, and then the electrons in this carbon hydrogen bond are going to go here to form a double bond here. So if I form a double bond here, then that means that this carbon is going to get 5 bonds. Well, we know that's not possible. Carbon cannot have 5 bonds. So I need to lose a bond. Well, what's the best thing to leave? Bromine is the best thing to leave. Bromine's a great leaving group. So bromine is going to leave and get rid of that extra bond. So that way I don't have 5 bonds anymore, right? So now I'm going to form my product, which again, this is just a 1-step reaction, right? So it's very quick. So I make a double bond there. And then I also get CH3OH. I get a protonated methoxide, which is just methanol. And then I also get my leaving group bromine, or Br minus, right? Okay. So this is the entire mechanism, right? So this is my major product right here. You'll notice I said major product. We're going to talk about what that means in a second. So this is the major product, okay? Now, I said that I could take a hydrogen from here as well, right? There's nothing wrong with taking a hydrogen from here, but there's a reason that we take a hydrogen from here less often, okay? And we'll explain why. So if I take a hydrogen from here, let's say that I did, right? So I have this and then I take a hydrogen from there. So if I took a hydrogen from here, then I'm going to get a double bond here instead, right? So if I took this hydrogen, then these electrons would go on here to make a double bond and then bromine would leave. So I'd get a double bond here. Now let's take a look at these two. I have this one versus this one, all right? How do I know which one I form? Well, earlier I said that in an E2 reaction, the Zaitsev product is going to be formed as the major product unless the base is bulky. Well, this base is not bulky. We'll see a bulky base later, but this is not a bulky base. Just know that. And so since this base is not bulky, we form the Zaitsev product. What is the Zaitsev product? Well, there's the Zaitsev rule, which tells me that if I have two different alkenes, the one that is more highly substituted is going to be formed more often, okay? So if I look at the thing that I said is the major product, this one right here, this alkene, right, has 1, 2, 3 alkyl groups around it, right? There's 3 alkyl groups around this double bond, okay? Whereas if I look at this double bond, I just have one alkyl group, right? I just have one thing attached to this double bond. The rest of these, I have 3 other hydrogens that are attached to this double bond. So which one is more highly substituted? This one is more highly substituted, right? Compared to these two. So this one is more highly substituted. So I'm going to form this one more often, right? This is the Zaitsev rule tells me that this is going to be the product I'm going to form. So this is also called the Zaitsev product because it follows the Zaitsev rule, all right? But my minor product is going to be this one. So this one's going to be minor, all right? And this has a name. This is the Hofmann product. So let's just think about this. So if the Zaitsev product is the product that is most highly substituted, right? This one has 3 things around it. It's more substituted than this one is. So the more highly substituted thing is the Zaitsev product. The less highly substituted thing, which is this one, or thing, I should say alkene, the less highly substituted alkene is the Hofmann product, all right? So whenever I use a regular base, I get my Hofmann product as the minor product, and I get my Zaitsev product as the major product. All right. So that's what's going on there. Okay. And the reason we get this Zaitsev product more often is because this is more stable, right? This double bond is more stable because all these 3 alkyl groups around it have hyperconjugation, and they can basically kind of donate electron density to that double bond. All right. So hyperconjugation is why we get the Zaitsev product more. That's why it's the major product in this case. So hopefully that makes a little bit of sense whenever we look at this. So again, with a non-bulky base in E2, we are going to get Zaitsev product as major, Hofmann product as minor. So now you may be asking yourself, is there a way that we can get the Hofmann product to be the major product? There is. So let's take a look at that next. So go over here. So let's say I wanted to get the Hofmann product as the major product. So there's a way that we can do that. So I'm going to use the very same thing. Use this again, same alkyl bromide. And instead, I'm going to use a different base. So we're going to use something called a bulky base. So the bulky bases, there's 3 that we need to be concerned about, all right? So there is potassium tert butoxide. So potassium tert butoxide looks like this. So it's an O- with a potassium. So this is potassium tert butoxide. There is also two others, okay, that we need to be concerned about. There's way more than just these, right? But these are the ones that we're going to be concerned about in this class. There is lithium diisopropylamide, which is LDA, okay? So LDA looks like this. So diisopropyls, there's two isopropyl groups on, and there's a lithium with it as well. So this is lithium diisopropylamide. So this is LDA. And then we also have lithium hexamethyl disilazide, which is LiHMDS. So what that looks like is an N with two silicons that have three methyl groups attached. And then I have lithium. So this is LiHMDS. So lithium hexamethyl disilazide. All right. So these are my three bulky bases that I need to be concerned about. All right. So in this case, I'm going to use potassium tert butoxide. Okay. So K, O, C, CH3, 3. And then remember that this is E2, right? So my solvent is just going to be the protonated version or the conjugate acid of my base. So tert butanol is going to be my solvent in this case. Okay, so now again, the mechanism's the same as it was, right? The mechanism doesn't change. So again, all that's going to happen is I either take a hydrogen from this carbon on the right, so I'll write it over here. So I either take a hydrogen from here, or I take a hydrogen from here, right? And my bromine will leave. So in order to take a hydrogen from either of these sides, like let's take a look at potassium tert butoxide, right? This is big. This is a huge thing. It's bulky, right? That's why it's called a bulky base, okay? So these bulky bases are so big that in order for it to get all the way over here to this hydrogen that has two methyl groups around it, this bromine and all this other stuff, it's hard for it to do that, right? It's very tough for it to do that because it's so big. So it's hard for it to get in here and get this hydrogen. Whereas whenever we had the methoxide in the last example, it went in there no problem. It was quick and easy, right? But in this case, this bulky base cannot take this hydrogen. It does sometimes, but it's rarer, right? It's not as easy for it to do that. So instead, it's going to take a hydrogen from over here instead. So it's going to take one of these hydrogens. Why? Because look, there's nothing around these, right? It can very easily come in here and take one of those hydrogens. Even though it is bulky, it can come in here and take one of those hydrogens, and then those electrons go on there just like last time, and bromine leaves. So then that's going to give me this. And then I also get my bromide. And then I also get HO. I get terbutanol, right? So I get these three things. Okay. So, but now you'll see that instead of forming what I formed earlier, instead of forming that Zaitsev product, right, I formed the Hofmann product this time. So I formed this as the major product. So this is major, even though it's the Hofmann product. And then I do get the other one. I do get the Zaitsev product, but it's minor. So this is minor, but it is the Zaitsev product. Okay. So basically what I'm trying to get across is that if I use a regular base that is not bulky, so if I use any base other than these three, okay, so if I'm not using potassium tert butoxide, LDA, or LiHMDS, if I'm using any base other than that, then I get the Zaitsev product as the major product. I get the more substituted alkene as the major product. because the smaller bases have no problem going in there and getting the hydrogen that has more stuff around it, right? However, if I use a bulky base like potassium terbietoxide LDA or LiHMDS, then I'm going to get the Hoffman product as the major product. I'm going to get the less substituted alkene as the major product because these bulky bases are so big that they have a very tough time getting to these hydrogens here, right? That's very difficult for them to do. So it's a kinetics thing, right? It takes a long time for it to get in there and get those hydrogens. So that's why it's not going to do that. So bulky base, major product is Hoffman. Non-bulky base, major product is Zaitsev, all right? So if on an exam you saw something like just a regular base and he says, draw the major product, then I'm just going to write the Zaitsev product. I'm not going to draw the minor product unless specifically asked to, right? If he says draw all products, then I'm going to draw the minor product as well. But typically I'm just going to be drawing whatever the major product is. If I see a bulky base reaction like this one, then all I'm going to write is my major product, which is this one, okay? This is all I would write as the product, okay? Unless specifically asked to draw the minor product, all right? Okay, very good. So hopefully that was instructive, a little bit helpful there. Let's go over here. There's a couple other things that I would like to do whenever it comes to these reactions here. So, all right. So the only other thing that I mentioned at the very beginning was that the hydrogen and the halogen that are, well, the hydrogen that's being taken and the halogen must be anticoplanar, antiperiplanar, 180 degrees apart, right? Okay, what does that mean? All right, so let's take a look at that. So let's do an example. Let's say that, oh, I don't know. Let's say that we're going to have a chiral molecule like this one. Let's take a look at this one here. Then, so I have an ethyl group here, CH3, phenyl, another CH3, and then my halogen, my chlorine. All right, use chlorine in this case. Okay, so I have an ethyl group, methyl, phenyl, chlorine, hydrogen. Okay. So in order for an E2 reaction to work, I need to make sure that the halogen and the hydrogen are anticoplanar. So we're going to have to look at this in a Newman projection to fully understand what I'm talking about, but we're going to put this through an E2 reaction first. So again, I know this is E2 because my solvent is the conjugate acid of my base. And this is also a tertiary alkyl halide, right? So there's no way this is going to go through SN2. Okay, so this is what I got going on. All right, so let's draw the Newman projection looking down this bond this way. Okay, so my front carbon is the carbon that has the methyl group and the chlorine and the phenyl on it, right? So let's take a look at it. So my phenyl is kind of going up, right? So pH is going to be here. CH3 is on a wedge, so if I'm drawing it in this Newman projection, it's going to be on the left side. And if you're having difficulty seeing this, I would most certainly make a model. Okay, so if you have trouble with Newman projections, then I would definitely make a model, and I think that'll make these a little bit easier to understand. Okay, so then that means the chlorine is going to be on the right side on the front carbon, and then we're going to draw this in staggered conformation. Then we're going to draw the back. All right. So what's on the back? Well, on the back, I have a ethyl that is on the left side. So I'm going to write ET on the left side. And then I have a CH3 on the right, on the dash, and then a hydrogen going down. Okay. So what do I mean by 180 degrees apart? Well, let's take a look at this. So you see this phenyl right here. Okay. That phenyl and the H are 180 degrees apart, right? This chlorine and this ethyl are 180 degrees apart, right? They're anticoplanar from each other, right? This methyl and this methyl, anticoplanar, okay? So that's exactly what I mean. So in order for an E2 reaction to happen, I need to make sure that the hydrogen that I'm taking, this would be the hydrogen I'm taking, right? And my chlorine, in this case, are opposite each other. Well, are they opposite? No, they're 60 degrees apart right now. So I need to make sure that they are opposite. So I'm going to have to rotate this front bond to make sure that they are 180 degrees apart. Okay. So I'm going to have to rotate this front bond 120 degrees. So what I'm going to do is I'm going to rotate this up here, this to here, and this one over here. Let me not draw that through the hydrogen, sorry. And this one over to here, okay? So I'm rotating all these 120 degrees, all right? So I'm going to redraw it here with everything rotated. So chlorine is going to go where phenyl is. Phenyl is going to go where CH3 is. And then CH3 is going to go where chlorine was, all right? And then the back carbon doesn't change. The back carbon stays the same. And it doesn't matter which carbon we rotate. I could have very easily rotated the back one as well, but I think it's easier to rotate this one. I think it makes it a little bit more clear. Okay, so now chlorine and hydrogen, you see how they're opposite each other, right? You see that they're 180 degrees apart. They're anticoplanar. So now my base has no problem coming in here. My OCH3 has no problem coming in here, taking this hydrogen. Those electrons are going to go and make that double bond, and then chlorine is going to leave, okay? So that's kind of how we draw the mechanism in there. It's kind of a mess, I know, but that's how we would draw the mechanism for that. And chlorine leaves, right? Okay. So what does that mean the product is then? Well, remember that this is all happening in one step. And let me move this over slightly, sorry. This is all happening in one step. So if I take a look at this, right, on the front carbon, which was this carbon right here, I have a phenyl and a CH3. So I'm going to put phenyl here and CH3 here, all right? And then I form my double bond here. Now, this phenyl is opposite or trans to this methyl group on the back, right? So this phenyl and the methyl group are trans. So in the product, I need to write them as trans, right? So whatever's going on here, I need to write that in the product. So this phenyl and this CH3 are trans from each other. Also, this CH3 and this ethyl on the back carbon are trans from each other. So I'm going to write ethyl here, okay? So this is my product. This is the only product I form, okay? So if I flipped CH3 and ethyl here, it's wrong, okay? If I flip CH3 and phenyl here, it's wrong, okay? So I only make, this is cis, right? I only make this cis product. That's it. Why? Because H and Cl had to be opposite each other. This is the only conformation where H and Cl are opposite each other, okay? So in the product, this is exactly what I'm going to get, all right? The cis product, all right? So we need to make sure to pay attention to that. So whatever your Newman projection looks like whenever the hydrogen and the chlorine are anticoplanar, you know, whatever's here and is trans to this, it needs to be trans to that in the actual alkene, okay? So make sure to pay close attention to that because it's going to be very important, all right? Okay, so now we've done this in a linear molecule. We also need to very quickly talk about rings, okay, unfortunately. So let's take a look at a ring. So let's take a look at this one. So I have my 6 carbons. So this is what I got here. So I have an isopropyl group and a methyl group and then my bromine. Okay, and they're all in a wedge. And then I'm going to put this through E2. So we'll just do NaOH and water. Sure, why not? Okay, so this is going to be my reaction that I'll be doing. Okay. So now, what I need to make sure about is that the bromine and the hydrogen that I'm taking are trans from each other, right? They need to be anticoplanar, okay? So if I'm going to draw this in a chair conformation. So I'm going to go over here and draw this in a chair conformation really quickly. So this is my chair. Not a great chair. I'll redraw it. A little bit better. Okay. This is my chair. Sorry. So I have water on bottom. So this is my chair. And so if my bromine here has to be trans from something, in order for this reaction to work, in order for an E2 reaction to work, the bromine has to be on an axial bond. Okay. It has to be on an axial bond. So I'm going to draw this bromine on an axial bond. It's on a wedge, so it has to be on an up axial, right? So up axial bromine. Okay. So then that means that this isopropyl group is going to be up as well. So that means that the up bond here is an equatorial, right? So it's on an up equatorial. And then this methyl group is here and it's also up. So this methyl group is on an up axial as well. Okay. So this is my chair conformation for this. So now the only hydrogens that I can take, again, are hydrogens that are 180 degrees apart from my leaving group, right? So you can do a Newman projection on this and make sure that this is correct whenever if you want to do a Newman projection on a chair conformation. But there's two hydrogens here, and then there's a hydrogen here. Okay, so this is an up equatorial, so that means the hydrogen's on a down axial. This is a down axial, and this is up equatorial, right? So I have two hydrogens here, one hydrogen here. And remember that E2 wants to take the hydrogen that's going to form the most substituted alkene. So I want to form this alkene. I'm going to draw it. Whoop. I want to form this alkene. This is the alkene I want to form because this is more substituted, right? If I formed this alkene, if I drew a double bond there instead, right, on this side here, if I wanted to form that alkene, that's not most substituted, right? This is tri-substituted. This would be di-substituted if I formed an alkene there. So I want to form this one. So the question is, can I form that one? Well, in this case, I can. Why? Because this is up axial, this bromine, and this hydrogen's on a down axial. So they're 180 degrees apart. It checks out. It's good. So in this case, my OH would come in, take that hydrogen, that would go there, and then bromine leaves, right? So then that would get me this alkene, okay, if that happened. I could take a hydrogen. I could take this hydrogen as well, right? I can take either of these, this one or this one. I could take either of these hydrogens, but I'm going to take this one because I want to form the most substituted alkene, right? However, this is the last example here, but I want to take a look at this. So all I'm doing is switching the isopropyl to a dash, leaving everything exactly the same. Okay, leaving everything else exactly the same. So now let's go ahead and draw the bromine again in the chair conformation on an up axial. So if it's on an up axial, then that isopropyl has to be on the down axial, and then the methyl group doesn't move. It stays the same. Okay, so now my hydrogen here is on an up equatorial, right? Well, this bromine and this hydrogen are not 180 degrees apart, right? So I can't take this hydrogen anymore. So that means the only hydrogen that I'm left to take is one from one of these two carbons. So I can only take this hydrogen. That's the only one I could take, right? So again, hydroxide is going to come in, take this hydrogen. Those electrons are going to go there, and then bromine leaves, all right? And then that's going to get me this. That's the only thing I form, right? This is my only product. So that's going to get me that. All right. So hopefully these chair conformations, it makes a little bit of sense. The only other thing that I want to mention here, and I want to mention something about this Newman projection one and the chair conformation one. Okay. So with the chair, you don't necessarily need to draw it. Okay. I think it makes sense whenever you draw it. I think it helps to draw it, but you don't necessarily need to draw it. Let's take a look at this first one here. So this hydrogen here is on a dash, right? And then there's a hydrogen here on a wedge and here on a dash, okay? So the rule of thumb is that if my bromine is on a wedge, then I can only take a hydrogen on a dash, right? So think about that, internalize that for a second, because it makes sense if you know that the groups have to be anticoplanar, right? They had to be opposite each other. So if bromine is on a wedge and hydrogen's on a dash, they're opposite, right? So that means that I can take this hydrogen or I can take this hydrogen. I can't take this hydrogen because it's on a wedge, right? So this is the shortcut, all right, without having to draw the chair. So, but I think it's important to know how to draw the chair because drawing the chair may come up on the exam, but this is how you can do it quickly without drawing the chair, okay? So again, if bromine's on a wedge, I can only take a hydrogen on a dash. Well, I can take a hydrogen from here or here. So in this case, I'm going to want to take the hydrogen from here because that gives me the more substituted alkene, right? This is my major product. I also take the hydrogen from here to get the minor product, the Hoffman product, but I'm not going to draw it because I'm just worried about drawing the major product. Okay. The other thing that I could do is I could look at this one, right? So if I look at this, then I have a hydrogen there on a wedge, and then these two hydrogens stayed the same, right? So now bromine and hydrogen here are both on a wedge. Well, these can't be opposite each other because they're both on a wedge. So I can't take this hydrogen anymore. That one's out of commission. I can only take this hydrogen. That's the only one I can take, right? So if I take this hydrogen, then I'm going to form the double bond here. And this is literally the only product I can form. So this is not only the major product, this is the only thing that I form in general. Okay. So that's all I can do. So if you don't want to draw the chair, this is a good shortcut. All right. So again, if bromine's on a wedge, I take a hydrogen on a dash, right? The opposite would be true, right? If my halogen is on a dash, I take the hydrogen that is on a wedge. Okay. So those just had to be opposite. They just had to be trans from each other in a ring. Okay. The other thing I want to mention here about this one that we did the Newman projection for, if you're having trouble with Newman projections, I would encourage you to use a model, but if you don't have a model, you don't need necessarily to do the Newman projection, okay? What I can do, so this hydrogen right here is in the plane of the paper, right? Or the screen. It's in the plane of the screen, this hydrogen, and it's going down. So without even drawing the Newman projection, I know that the other thing that is in the plane of the screen that's going up is opposite to it, right? So all I need to do is get chlorine where phenyl is. Okay, so if I get chlorine where phenyl is, then that'll get me to where I need to go. So if I rotated the front one without even doing the Newman projection, right? I rotate the front one. So I'm going to move this one here, and then move this one here, and then move this one here. Okay, so chlorine is going to go where phenyl is. And then phenyl is going to go where CH3 was, and then CH3 is going to go where the chlorine was. Well, now these are opposite each other. So now I can very easily take this hydrogen and then form my double bond here, okay? And now I can still figure out what's going to be trans where. So this phenyl is going to be opposite the CH3 in the product, right? Because this is on a wedge, this is on a dash. These are going to be trans. And then same thing here. This methyl that is on a dash is going to be opposite this ethyl that's on a wedge, right? Because these are opposite each other. So just like I drew in the product. So that's one way that you can shortcut this without having to draw the Newman projection and go through all of that. So if you just want to rotate it the way that it is and then just know what's opposite what, just by looking at it, you can do that. Same thing here. If I want to just take a hydrogen that's opposite my halogen without having to draw the chair, you can do that and that'll work. But these are the full explanations of everything. Okay. So that's everything about E2. All right. So I appreciate you watching this. And in the very next video, we're going to be worried about E1 and those reactions. So hopefully you'll join me for that. I appreciate it, and I will see you then.